Okay, let me see. Window. This one. And let's see, how do I? This way. 有什么隐藏的一些？Okay, I guess this works. How do I? Okay, so I guess please go back to the seat quickly. Yes. Hopefully everyone pick up. 没有拖音。不显示。Okay, now this one. This one. 我想同学可能先就做吗？那个我们考卷之后拿也可以。对，抱歉比较晚下来。Okay, so let's go over the midterm problems. So this should be relatively quick. So I guess people are doing very well here. Maybe it's a bit too easy, or maybe you guys study very hard. But anyway, the average is 88, and yeah, so a lot of people get close to a full grade, and I guess that's good for you. Yeah. So anyway, we'll go over the solutions here. Midterm 2, and yeah. So first question. This is a bit similar to what I've done before. So it's a kind of question where you take the difference of your signal and you calculate the Fourier transform of the difference, and you go back to the Fourier transform of the original signal x of t. And yeah, so this is very similar to the so in the continuous case, we had those quadrant where your signal look like this, and you take a derivative, so your signal look like this. Then you do Fourier transform and go back, and this is basically a discrete version of that. Okay, and yeah. So let's go through this. And so our signal is this, so it's a lot of 0 and 3 ones. Oh yeah, and once again, so there are people who doesn't follow the difference and the go back thing, but I think it's better to follow what's described here, but we didn't take off the points if you just do the Fourier transform of this directly. And actually in this case the Fourier transform of this is not too bad, because we set our x of tn to be a very simple function and only have 3 spikes here. But anyway, x of n, look at this, is a lot of 0 and 3 ones. It's a period 10 and a discrete time function, so it's a lot of, so it has 7 zeros and 3 ones, and then 7 zeros, 3 ones, etc. So it's periodic with period 10 and it has 3 1 here. So first we take g of n as the difference of x of n. And because x of n is a lot of constant everywhere, so only a difference happening is here and here, right? So G over n, so this is x over n, and G over n will have let's see, xn minus xn minus 1. So you will have 1 at this 7 point, and minus 1 at this n point or 10 point. Okay, so that is G of n. And then the first quadrant is asking you to show that G of n has a fundamental period of 10. And so there is a little tricky here. So it's easy to see G of n has the same period as x of n, because x of n has a period 10. So this has a period 10, this has a period 10. So if you just go through this equation, you see that G of n also has a period 10. But you also need to prove that this is a fundamental period, so you need to show that there is no smaller period, and there is not much, no very smart way to do this. Basically, you want to write down G of n, and you look at it like this, and you find out that in this period of 10, there is only, so maybe in this period of 10, there is only one place where it has negative, so it's impossible to have a smaller fundamental period, because you shift it around, you will shift this negative spike, and so G of n cannot have a period smaller than 10. So the period 10 is the smallest period. Okay, so it's very easy. And then, as we say, we want to determine the Fourier coefficient of G of n, and they really only have 2 spikes, and so we know the Fourier coefficient of the delta function, and the Fourier series coefficient of the delta function should be just 1 over the period. It's 1 over 10. And then there is another time shift of this delta function, and you can apply the time shift formula to get this HR e to the minus jk jk not this is e to the minus jk omega excuse me, jk omega naught not is a little weird. Oh no, yeah. So the omega naught is 2 pi over 10, and naught is 7, so you get 7 pi over 5. And also you can also just do this brute force calculation to get this result. Okay. And finally, now that's the tricky part. So we have the G over n being the difference of x over n, and we want to go back to find out the Fourier coefficient of x over n. And so what do is we do the first difference equation. So we say, so there are 2 ways. You can do first difference, or you can do the accumulation formula. So let's see our table here. So we have the first difference. So if G is the difference of those, so the coefficient of G will be 1 minus e to the jk omega, not the coefficient of x. And or you can just think about x as the running sum of G, and you will get this formula. It's just a back force of sensing. But anyway, so here is bk are the coefficient of G, and by the first differential formula, we know bk is this 1 minus e to the jk omega naught, the coefficient of a. So you divide things back, and you just get ak equal to this whole thing. And and here we are doing a very easy case, right? Because we already assume k not equal to 0. So we are not dealing with a singular case. And so as an extra quadrant that we didn't have here, so remember before we had, when we do this, so this versus this, right? When we do those 2 things, we have that for A0, we need to do special case, and here is the same thing. So if k equal to 0, then this thing doesn't work, because you will get a 0 here. So you cannot get A0 from B0. And for A0, anyone to answer? Or what should we do to get A0? No? Okay. Yeah, so A0 is in this case. So A0 doesn't depend on B0 at all, because x of n you can shift by arbitrary constant, and that doesn't change u of n at all, right? Because it only takes a difference. So A0 you need to calculate from x of n directly, and you just take the average of x of n here. And so A0 will be average of x of n, and it is 3 spikes over 10. So A0 is just 3 over 10 if you want to calculate this. And this is one of the quadrant you do in midterm 1. Similar to one of the quadrant in midterm 1. Okay. So any question? Should we? Okay. And this is a slightly tricky quadrant. Then the next quadrant, okay, now it's getting very easy. Okay, so next one, basic calculation of Fourier transform. So the first one is Fourier transform of periodic function. And so trick point here is periodic function, so you should get some delta function in your Fourier transform. And so you can either just look at tables. I think we have sine and cosine here. So in here, the answer here we are just using, we look up the table for sine and cosine, and there are those things, and but there is some time shift on your side, and and yeah, so you deal with the time shift on your side, you get extra e to the j to omega over 5. Or you can even do more brute force way, so you can break a cosine t into e to the jt plus e to the minus jt and 1 over 2. And you can break your sine t to e to the, okay, so it's actually sine phi t plus 2 to e to the j phi t plus 2 and minus e to the j minus phi t plus 2. And you just apply this e to the j omega naught t formula to everything. Okay, and this should be 1 over 2i, 2j, I believe. Yeah. Yeah, so you can do this also, and so you will get the same delta function, and here you will get, so you will probably not get this thing, but it's the same. So you will get e to the 2j here. Excuse me. So from here, so this extra 2. If you just break your sign into e to the j and e to the minus j, then here you will get e to the 2j and e to the minus 2j. And it's the same thing because this omega here will get picked up by the delta function. So if you multiply this omega on this delta function, you will have this omega equal to 5, so that'll give you e to the 2j. And on here you will get omega equal to minus 5, so e to the minus 2j. Okay. So that's pretty easy. And next one is also a very familiar function, right? So it's two-sided decay. So we have this nice picture here. Is two-sided exponential decay with rate 3, and its peak center at this t equal to 1. And we're basically already seeing this two-sided decay. But so there are multiple ways to pierce this around. You can either do time shifts to shift your peak at the center to this 3 and the minus 1. So this is kind of what we do here. Or you can do direct calculation by just doing the integral, because this exponential decay integral is not too hard. But okay, so let's go through a little of the calculation. Maybe let's see this time shift. So we say is 1 decay. Is 1 decay center on 1, and okay, so we have this y is this decay with rate 3, center around 0, and then we say x of t plus 1 is this. So we do time shift on x, and then we add up the positive side y and the negative side y. Okay. And so this is e to the minus 3t u of t. We already know this transform very well. is the thing we do partial fraction all the time is 1 over 3j omega. And then if we do time negation, obviously we take time negation. And then here we are saying, let's see, makes sense. Okay, so we are saying if we put t plus 1 here, it will cancel this negative 1. So x over t plus 1 should equal to e to the minus 3 of the value of t. And then we use the time shift formula. And so if we do Fourier transform on x of t plus 1, let's see if we can just look at the table here. Okay, yeah. So if we do Fourier transform of x of t plus 1, so it's this minus t0 with t0 equal to minus 1, so you should get HR e to the j omega. So e to the j omega. Oh. Okay. And yeah. And so you have this HR e to the j omega side on this side, and this 1 over 3 plus j omega, 1 over 3 minus j omega. Oh yeah. Yeah. And so you just divide this e to the minus j omega to the other side, then you get this as the answer. Okay. And you can also just do the integral, and it should give you the same answer. And wait, are we missing a problem? No. Okay. That's problem 2. Any question? And then problem 3. And 3a is actually a little tricky because if you try to do time shift, I'm not sure you can do. You can maybe do it. So if you just do Fourier transform for u and u, you probably get a very weird answer because u has the the Fourier transform of u has the annoying delta function. But if you think about what the function look like, then it's a lot easier because you take the difference of those two unit step functions. Think about, although it's discrete time. So it's a unit step function starting from 0 and a unit step function start from 2. And if you take the difference, then it's just 2 spike at 0 and 1. Yeah. And yeah, then you do the Fourier transform of the 2 spike is easy, it's just this 1 plus e to the minus 1 plus e to the minus j omega. So yeah, so it's easy if you think about how this function looks like. And the next one looks a little harder than it should be. So it's a function that looks like this. So n from is x over n equal to n from minus 3 to 3. So it's this. And 1, 2, 3, and minus 1, minus 2, minus 3. And you might want to do like a differentiate on this, but turns out it's easier to just do this with brute force formula. So if you do this by just brute force calculation, and you find out there are only 6 spikes, and you can do the Fourier transform of those 6 spikes. So this plus 1 minus 1 give you this e to the j omega minus e to the plus j omega, and plus 2 minus 2 give you this 2 e to the minus 2 j omega and minus 2 e to the j2 omega, and you have the plus 3 and the minus 3. And so you just have those 6 terms, and you see you can also simplify them a little bit, because you have this e to the omega, e to j omega minus e to the minus j omega, so that should give you a sign. So you have 3 pairs of sign like this here. And okay, so Zijing said, I believe you can also do the hard way, and which one do you use? This one difference? I believe if you if you use this one, and if you use this one, and so you start with like a square wave, right? 1, 2, 3, 4, 5, 6. You start with this, and you do dd omega, right? So if you do this you do dd omega, then you can get back this, and then I guess you try to integral back omega. So this should give you omega like sine omega over sine omega, I believe, right? And you say, oh, okay, so you just do the dd omega on this thing, and you will get this, and hopefully you can clean all this back to just 3 sine 18 together. So that's theoretically right, but unfortunately it's harder in calculation. Okay. Okay, question. Okay, then the next one. The next one is basically same as this 2a. So once again, we have a periodic function and we want to do Fourier transform, but it's now discrete time. So we have this sine pi over 5 and the sine pi over 3. And oh yeah, a little confused. Sine and cosine. Anyway, so I think we can just look up table here. So those sine and cosine and they can once again basically break into e to the j omega n plus e to the plus minus e to the minus j omega n, right? Those kind of things, and so that will give you delta functions on the frequency domain. But now it's discrete time, so those delta functions should repeat every 2 pi, so that's why you get this extra 2 pi k here. And you can also look up table, and you should say, yeah, you get this 2 pi over here. Okay, and omega naught. Yeah. And here our omega naught. Okay, are we? Oh, over AK. Yeah. So that's this. And here there are little things to check. So we need to make sure that this is actually a periodic function. So so this should be rational 2 pi, and that should be correct. So omega naught here is this. So I guess we can check like n is. So this is n should be like 2 pi divided by omega naught, and times some m, right? And so we have 2 pi divided by omega naught, and we get this is 10, and this is 6, and so you see that we have an integer. We have an integer period, and that's correct. And so a quadrant that the textbook has, but I think is you define is what if you have cosine n here instead of cosine pi over 3n here, and that becomes a periodic function. And yeah, so here you will have that omega naught over 2 pi is irrational. Then x of n is a periodic function, and I believe if you try to find the Fourier transform value periodic function, then you cannot just plug in this formula, and that's actually something that doesn't converge. Okay. So any question? That's a weird one, but when you plug in this formula, be careful to make sure that when you are discrete time, you actually get a periodic function. So this will be periodic. Okay. I've not. Okay, so the next one, problem 4. We're on schedule. So problem 4. This is a question. So it's more on continuous Fourier series, but I believe the filter is also in our scope. So this one you basically just need to understand what the filter do. and we have this high pass filter. This is oh, okay. Yeah, we have this high pass filter. That says that let's draw this high pass filter, and it pays if your omega is bigger than 20. Okay, that is the h of j omega, and on your omega axis. So if your omega is more than plus minus 20, your filter pays through. And we are saying that we have a periodic signal, with fundamental period is t equal to power 3, and so so it's a periodic signal, and so it's on frequency domain. You will have some spikes, some delta function, right? And we're asking this delta function filtered by this h of j omega, and then we find out that on this high pace field function, then everything actually pays, because it says that after you do this filter, it's still x of t. And we want to ask, like, then if everything pays, then the low frequency one should be 0 in the beginning, right? So for those AK, excuse me, yeah. So x of t has all those frequency for different k, so this k equals 0, and then 1, 2, 3, 4, 5, 6, etc. And so the idea here is that if AK is small, and so the small AK should get filtered out by this high pass filter, but it didn't get filtered out because we say that after the high pass filter, the signal is still x of t. That means those AK are starting with 0 in the beginning. Yeah. And so the only calculation basically we need to do is we need to find out what's this interval here. So how big is our omega 0? And so omega 0 obviously is just 2 pi over t, and it is 6. And so we know that, so we should actually draw this a little better. So we know that omega 0 is 6, and so k equal to 1, it will be a spike at 6, then k equal to 2, so it's k equal to 1, k equal to 2, will be at 12, and k equals 3, or at 18, and then and the next one will be 24, and 24 will be paced by the high pass filter, so it's okay. But we know those k equal to 1, 2, 3 should be starting at 0, and also k equal to 0, and negative 1, negative 2, negative 3. Okay. So yeah, so the calculation is very easy, and you just need to understand high pass filter. And so it says that if your signal pays a high pass filter, and so all the high frequency component you can have in starting, you can have those high frequency component to start with, but you must start with no low frequency component, so that after the high pass signal you don't get those filter out, because you don't start with them anyway. Okay, question? Okay, and then the next one is the property question. So we have those three conditions: x of t being real, x of t is 0 for t less than 0, and this weird equation here. And we're asking you to find the closed form expression of x of t. So that means you want a closed form expression. I think some of you have a question on, but it just means that it's like a explicitly write down mathematical form. Okay? So like a formula that everything is calculated out. Anyway, so I think the hardest step is the one where you use x of t is real. And x of t real, use this, and I believe it's probably not in a property. but the x over t real, we will have, okay, maybe write this, x dot of j omega equal to x over minus j omega, right? Minus j omega. And so if you look at this, and then you will see that the real part of big X is the real part when these two equal is even, and the imaginary part of big X is odd. Okay? And this is what we use. So the real, because X is real, then the real part of X is even. And we know that always the even part of X always go to the even part of the even part of small x always go to the even part of big X, and that means the even part of X will go to the real part of the big X if X of t is real. Okay. And, so this is the most important part you need to start with to be able to do this. And some people seem to be using this, but they didn't write this like from 1. And so I think our homework we are a little lenient on writing the logic correct, but this is quite important here. So if you don't write this, I take out 1 point. Maybe I should take more, but so if for the final, I think if you are doing this logical derivation question, you need to make sure to write down the reasons of why things are true. Okay. So here is important that only when x of t real, you have this even part of small x go to real part of big X. And from here, then you can use 3. And 3 looks like a lot, but if you compare it to just the Fourier transform equation, I believe. Okay. And yeah, so just look at this Fourier transform equation, and you see that this is basically Fourier transform equation bound on the real part of big X, or the inverse Fourier transform equation. Okay. So this is really just the inverse Fourier transform of the real part of big X. And we already said that the real part of big X to inverse Fourier transform to even part of small x. So this thing is the even part of small x. Yeah. And from here we're almost done. So we are done with the knowledge part, and we need to do a little bit calculation. And then finally we need to use the second one. So second one says that x of t is 0 on the t less than 0 side, and it is something on the positive side. And we say if you even this, it looks like this t to the minus 2t. And yeah, and so if you focus on the t bigger than 0 part, then you see that this even thing is the whole thing plus the negation of it. But for t bigger than 0, this less than 0 part is, well, is by definition, by the condition 2 is 0. And so for the bigger than 0 part, this even thing is just 1/2 of the whole thing. And you can also think about just a picture way. So your function should look like this. And if you just try to symmetrize this thing, then you will flip this around and add them together, divide by 2. And so you should just get something that's like this symmetric, but with height 1/2. Right? So if you try to even this thing, symmetrize this thing. And so you know this even thing should be on the plus side. If you just multiply by 2, you will get back the original function. Okay. And on the negative side, obviously it should be 0 as given. And so the whole thing is this, for t less than 0 is 0, for t bigger than 0 then it's twice this thing. And if you are being a little smarter, then you see that for t bigger than 0, you don't need to put absolute value sign, so it's like this. Or you can write this whole thing, I guess, in a more close form, such that in one equation, so you just times u of t. Okay. Okay, quadrant. Okay, then finally the last quadrant. I think we have done a lot of practice, so people are doing very well on this. And anyway, it's solving differential equation, and it's not too hard. So the first one, you write out big H, and you can basically just look at this thing and write down directly. So if you are very familiar with this, so you have this 2 here, then you have 2 here, then you have 156, then you have 156 here, with j omega squared and j omega and 6. And if you don't do this slower, then you say that you do Fourier transform on both sides, and you get a whole bunch of j omega polynomial, and you move things around, and remember big H equal big Y divided by big X, and you get this thing. Okay. And then the next one, we ask you to get a small h, and so we do the partial fraction expansion, and we get the number very nice here because we have 2 and 3 here, and so the difference is 1, so we just get the 1 and minus 1 by 2, so 2 and minus 2 here. Okay, and then you do inverse Fourier transform by using a table, or so although this a plus j omega we know very well is e to the minus a, and so you get e to the minus 2 and e to the minus 3 here with your 2 and minus 2, and obviously u of t. And the last one is a bit trickier, but also not too bad. So we have, say, our x is another thing that can be partial fraction, so e to the minus 2 u of t, and obviously big X is 1 over 2 plus j omega, and now big Y is big X times big H, and so you get this 2 plus j omega squared here. And yeah, so you get a square here, and then you need to break this thing. And I think a few people got this wrong, so that's just a calculation you need to be careful about. And also there are, I see that there are easier ways to do this calculation a bit easier. So if you break the 2 plus j omega and the 3 plus j omega part first, so if you start with this 2 plus j omega 1 minus 3 plus j omega over 1, and then you times 2 plus j omega, and so then you multiply those back, and so you see the square term is already this 2 plus j omega square, and then you break this 2 plus j omega and the 3 plus j omega again, and you get this 1 minus 1. Okay, and anyway, you got these 3 terms, and then you do inverse Fourier transform, and you do inverse Fourier transform, then basically you look at table. So those 2 terms you probably remember, so it's e to the minus a, e to the minus a, and this a plus j omega squared, you look at table, you find out is t to the minus a t. Okay, so that should be pretty easy. And then, oh, we have a lot of down here. Yeah, so we also have that in table somewhere, yeah, here. No, it's the wrong table. 4.2, right? So yeah, t to the minus at is this square thing. So it's also easy. Okay, and I believe that's it. So any question, or if there's no question, then we will finish the class here today, and we'll go back to our Laplace transform on Friday. Okay, and yeah, so if you haven't pick up your exam, you can pick up here. I think most people pick up. Okay, so see you on